Okay, so we're beginning our discussion of chapter 23. We talked about enolate chemistry and the reactivity and application of enolate alkylation reactions in synthesis. What we're now going to talk about is another facet of enolate chemistry, which are carbonyl condensation reactions. So let's review for a moment. When we think about carbonyls, it's important to note that depending on the reaction conditions, your carbonyl can serve as an electrophilic or nucleophilic functionality. When you have your normal carbonyl, your carbonyl carbon is electrophilic and it can react with many common nucleophiles via carbonyl addition reactions. So this is our carbonyl. In comparison, your enol, or in this case, your enolate, is no longer as electrophilic. When you deprotonate the alpha position of a carbonyl and you generate an enolate, this enolate is functionally nucleophilic and it can react with electrophiles as a carbon-centered nucleophile. So the carbonyl is an electrophilic functional group. And when you deprotonate the alpha position, you generate an enolate, which is nucleophilic at carbon. Does this discussion of carbonyl functionalities as both electrophilic under neutral conditions and nucleophilic when deprotonated or when treated with acid to convert them to the nucleophilic enol or enolate form? The carbonyl is an electrophile. The enol or enolate derivative of your carbonyl is a nucleophile. Does that discussion make sense? Okay, so as carbonyls can function as both nucleophiles or electrophiles, we can take carbonyls and subject them to reaction with other carbonyl containing compounds. This is the classic example of these carbonyl condensation reactions is the Aldol reaction. So we know that aldehydes and ketones ionize under basic conditions to yield enolates. So we can take a ketone, deprotonate the alpha position, and we can generate the corresponding nucleophilic enolate. This generated enolate, because it's a nucleophile, it can react with electrophilic ketones or aldehydes to yield a beta hydroxyaldehyde product known as an aldol product. So for example, if you take acetaldehyde and you treat it with sodium hydroxide, we can deprotonate our alpha position and generate an enolate. From here, our enolate can attack the electrophilic carbonyl carbon of your aldehyde or ketone to give a beta hydroxy carbonyl product. Now, generally, the aldol reaction and aldol reactions work best when the ketone or aldehyde used to generate the enolate is more acidic than the ketone or aldehyde reacting with the enolate, or the enolate is generated before the reacting ketone or aldehyde is added. So in the classic aldol reaction, you generate an enolate and that enolate attacks the carbonyl of either a ketone or an aldehyde. This forms a carbon-carbon bond and makes a beta hydroxy carbonyl compound. Does the general scheme for the aldol reaction make sense? So, building on this, let's talk about the mechanism of the aldol reaction. Under basic conditions, your base pulls off an alpha proton and we generate the enolate. From here, your enolate can attack an electrophilic carbonyl of a added ketone or aldehyde to make your desired aldol product. So we formed this carbon-carbon bond, and then after protonation of our generated alkoxide ion species, we've generated this beta hydroxy ketone compound. In this case, this is a beta hydroxyaldehyde because we used a starting material that contains an aldehyde. Does this mechanism for the Aldol reaction under basic conditions make sense? We generate our enolate, the enolate attacks the electrophilic carbonyl of our added ketone or aldehyde. Does this make sense to everyone? Are there any questions that I can address on this mechanism before we move on? Okay, let's talk about the aldol reaction under acidic conditions. In this case, rather than going through an enolate, we go through the corresponding enol tautomer. This enol tautomer is nucleophilic and it can attack activated electrophiles such as this protonated aldehyde. From here, once we've generated our desired beta hydroxy ketone, we're just one cleanup step away. After deprotonation of the carbonyl oxygen, we get our desired aldol product. Does this mechanism for the aldol reaction under acidic conditions make sense? Sure. Any questions I can address on this general aldol mechanism? Okay, so let's keep going now and let's try to apply what we've learned to predict the products from the following reaction and draw a mechanism for the following reaction. And one useful trick that's applied in the aldol reaction is that we use our electrophilic ketone or aldehyde, and we use an electrophilic ketone or aldehyde that lacks acidic alpha protons. So as we notice, only this ketone has available acidic alpha hydrogens. So as a result, when we treat this mixture of our ketone and aldehyde with base, only our ketone has alpha protons that can be deprotonated. Just as a reminder, LDA is a common strong organic base that's used to generate enolates. It's a very strong organic base that can be used to deprotonate the alpha position of a range of compounds. So, with this context in mind, let's try to predict the product from the following aldol reaction, and then let's try to draw a mechanism for this reaction. So, as we work through this example over the next 4 to 5 minutes, don't be shy to share your thoughts in the chat verbally or annotate it onto the class whiteboard. Does anyone have an initial idea? Does anyone have an initial idea for the proposed mechanism for this reaction? Would anyone like to share or annotate their proposed mechanism for this aldol reaction? So just in a big picture sense, if we take a ketone and we treat it with strong base, what are we going to get? If we take this ketone and we treat it with strong base, what's the first thing that we're going to see? So we have these acidic alpha protons. We have a strong organic base, such as LDA. So what will happen first? We'll pull off an alpha proton and we'll be able to generate our enolate. So the alpha protons are acidic. LDA is a strong organic base. So we can pull off our alpha protons and in turn generate our enolate. Okay, so once we have our enolate, what will happen next? We have our enolate floating around in solution, and we've treated this enolate with an electrophilic aldehyde. What reaction would we see, and what will our product look like? Would anyone like to draw out the next step for this reaction? So we have many students commenting that the nucleophilic enolate will attack the electrophilic aldehyde carbonyl carbon. And with that, we'd be able to form a carbon-carbon bond and generate our aldol product. Okay, so from here now,